let's discuss hard and soft ferroelectrics and materials. These names, hard and soft, are indirectly related also to mechanical properties. Those that are piezoelectrically hard will also be mechanically harder than soft materials, but there are a number of other characteristics which make us call them hard and soft. It is actually an analogy to magnetic soft and hard magnetics. However, the physical mechanism has nothing to do. There is no relationship between them. However, since people in electronics industry field are used to hard and soft magnets, then those terms at early days of piezoelectricity in 60s were also used. So what are soft materials? So soft materials have low coercive field, which means that they are very easily to polarize. But that also means that they are easy to depolarize. So if you apply a little bit of pressure on them, they would depolarize. Why should pressure depolarize a ceramic? Well, the pressure, since in ceramic, once it is polarized, most of the domain walls that are left are ferroelastic. Ferroelectrics, ferroelastic walls are very sensitive to external pressure, so they can orient. And since pressure is centrosymmetric, that means that you cannot make it more poled. You can only depole it. Well, this is a little bit tricky statement, but if you have a polarization like this and you apply pressure on it, it will do something like that. And that means that with respect to this phase here, the material would be depoled. They have large permittivity, which is good for many applications, large piezoelectric coefficients, but they also have large losses. So at higher frequencies, they would heat up easily. Now those losses, electrical losses, but also mechanical losses, are due to domain walls. You will see that domain walls in soft materials are very easy to move. They are responsible for all this, so it's not due to conductivity. And this easy motion, displacement of domain walls under external forces make materials to have large piezoelectric coefficient, large permittivity, to be mechanically soft, to have large losses, both dielectric and mechanical, are easy to pole and dipole, low coercive field. On the other hand, hard material have in general high coercive field, although this is a statement that's not, as you will see later, not really accurate. They need very large fields to open up the loops, but once open up, you will see that they have the same coercive field as a soft. So this is a statement that should be taken with a reserve. They have a lower permittivity than pure materials or soft materials, lower piezoelectric coefficients, lower losses, but somewhat higher conductivity. And they are difficult to pole. You need to pole them for a very long time with, in general, larger fields. And you will not, once poled, you will not depole them that easily. So there are applications where people prefer hard ceramics. Where you work with the large signals, with the high energies, then you would like to work with the hard materials. And where you work with the smaller signals and really need a very large response, but not that much stability, you work with the soft materials. And we will come through some examples of this later on. So let's see some characteristics. Let's compare these materials So here is piezoelectric coefficient as a function of dynamic pressure amplitude. This is a graph that I have showed you before. In a soft material, we have that we have a very large nonlinearity, large piezoelectric coefficient and a large nonlinearity, while in a hard material, we have a much smaller nonlinearity and much smaller piezoelectric coefficient to start with. And this immediately suggests to us that domain wall motion plays a role. Now, I didn't tell you, but difference between these two compositions is just that one of them has 1% of niobium and the other one has 1% of iron. I think that's the amount. It's the same composition otherwise. Zirconium to titanium ratio is the same. So it's not that they are coming from two different regions of a phase diagram. Same chemical composition, just about 1% of dopant. Now let's see what these dopants are doing. And it is also possible to have other dopants. You can produce soft materials by doping hard materials by doping on an A site, and it doesn't have to be B site dopant, but for a simplicity, I'm discussing these cases. So dopant can go on A site both to make material soft. For example, lanthanum on a PZT will make material softer, and for example, potassium on lead site would make material harder. What is important is to have donor and acceptor doping, rather than on which side dopant goes. But then again, for simplicity, I assume that we have this situation and where we are doping on a B site of perovskite cell, on titanium site. Now, there are several things I have to say here. If you have undoped material, it will behave as a hard material. So that also gives us some information about the mechanism. And let us now see what is the defect chemistry here. So when I put niobium on a titanium site, what happens? Valence of niobium is +5. Titanium is +4, which means that niobium brings 1 electron. However, so we mark it like this, it's negative. However, niobium is not going to be, on titanium site is not going to be compensated by, this would be +1. I apologize for that. So this would be +1. And then you would have either plus electron, 1 electron to compensate for that, or you would have some ionic compensation. And it turns out that in a PZT, this compensation is lead vacancy, which is -2, or we write it like this. So this is not charge neutral, and I will come to that later. Now, when we so why PZT prefers to have compensation with the lead vacancy than with the electron? Well, it turns out that it is very easy to replace, to get rid of lead in PZT. lead will easily evaporate. Some of lead vacancies are already present in a material when we start. Oxygen can be exchanged with the atmosphere, and it turns out, and we know that both empirically and from calculations and so on, that this is equilibrium defect concentration in a PZT. Now, what happens when we with the soft PZT, with the hard PZT, here we have iron on titanium side, and if iron is +3, and you can also have nickel and other elements, if iron is +3 and titanium is +4, this would be -1, or we write it like this. And then compensation again can be, for example, with the holes, but it turns out that it will be with oxygen vacancies, which are +2 charge, or we put these two dots. So I'm using here Kröger-Wink notation. I hope you are familiar. If not, please take a look. So this is Kröger-Wink Wink notation. So we believe that we know what is the defect chemistry in these materials, and this has been verified by electroparamagnetic resonance, by conductivity measurements, by annealing, and so on. It's pretty much clear that this is what's happening. But why does it lead to such dramatic difference in the properties if it is enough to put just 1% of dopants, or even 0.1%? And then why pure material behaves as a hard material? Now, once we know that we have lead vacancies for donor dopant, and that we have oxygen vacancies for acceptor dopant, these are keys. In undoped material, it is easy to understand that lead vacancies and oxygen vacancies may mutually neutralize each other. PBO is very volatile species in a PZT during the preparation. You mostly lose lead oxide. Lead is not going to go out alone. It will always go with the oxygen, and therefore you will have some percentage of lead vacancies and oxygen vacancies in the material. And since it is oxygen vacancy, which is intuitively somehow, which looks to us to be related to these hard properties, then it is understood why pure PZT, but defective PZT, behaves as a hard material rather than a soft. So it's not a lead vacancy which is important, but more oxygen vacancy. So let's see how can we approach this problem. Well, we can look in a two-dimensional representation of these two materials. So this is acceptor doped, this is donor doped. Here is iron on titanium side, which is negative. Here is niobium on titanium side, which is positive. We assume that titanium is surrounded by oxygen vacancies, and that niobium is surrounded by somehow lead vacancies. Now, there is immediately we see one big difference, and that is that these oxygen vacancies see a network of oxygen octahedra along which they can move. Okay? While it is much more difficult for a big lead or lead vacancy to move in the structure. It's a longer distance, and there is no this network as clearly defined as in the case of oxygen octahedra. So oxygen octahedra again play a role here. So let us see again what is happening. We will look at the hard materials, and from what I said so far, basically the mechanism that has been proposed and which has been widely accepted and confirmed with many experiments is the following. In a ceramic, we have a ferroelectric polarization, okay? And when we make ceramic at very high temperature, above, let's say, 1000 degrees, material is cubic, defects are randomly distributed, nothing happens. When we cool material, once we come to TC, the polarization sets in and the temperature is very high. Let's say for a PZT, it's 300 something degrees. So the oxygen vacancies are very mobile at those temperatures. Polarization sets in, and that polarization forces oxygen vacancies all to align in such a way. So if this is direction of polarization in surrounding lattice, the defects, which we have only one iron atom instead of titanium on 100 titanium atoms. So it's rather diluted. There is enough energy for this oxygen vacancy to align in a cell in which we have defect with those cells which don't have defects. So we will have alignment of defect dipoles and dipoles from a macroscopic, from the polarization, ferroelectric polarization. So these are defect dipoles, and this is the polarization in the cell. And imagine that we have here a 90-degree domain wall, and then that we apply that we apply electric field, and to move this domain wall down. So we are applying electric field in this direction. Now, to do this, normally if a material is non-defective, all we have to do is to move titanium from one potential well to another, and that's it. Here, the situation is much more difficult. Not only that we have to move this iron, which may not move at all because that unit cell, it's not even sure that it is ferroelectric. We actually have to rotate this, we actually have to rotate to move this oxygen vacancy from this position to this position or to this position. And that may require much more energy than just switching B ion from one potential minimum to another. So it will be very difficult to move domain walls. And what happens is that as soon as we remove this field, this domain walls snaps back. So these defect dipoles act as a restoring force to polarization. If polarization manages to move, let's say these titanium atoms around the defect forces them to go back to the initial position, because with these relatively small fields, oxygen vacancy doesn't have to rotate at all, to move to another position at all. Okay? So we have a relatively mobile polarization and relatively stiff these defect dipoles, which if field is not large enough, will force polarization, which rotates to come back to the old position. Now, if you apply very large field, then you will move both defect dipoles and spontaneous ferroelectric polarization. There is another factor here, and that is that around this oxygen vacancy, the lattice will be distorted. And it can be distorted two ways. If oxygen is missing here, then there is no negative potential of the oxygen atom between these positive lead atoms, and they can be either repelled, or because we have a one ion that is missing there, the lattice can actually become smaller there. And the different oxide materials will behave differently. So I actually don't know. Here it is drawn as though lattice will shrink in that position, but I think it's actually the opposite. It will expand. I think that's the case. In any case, all these defects, lattice cells, unit cells in which there is a defect, will also be elastic dipoles. Okay, they will elastically deform the space. So not only that we have here polarization of dipoles and ferroelectric distortion of the cell, but we also have elastic dipoles. So imagine that you have a homogeneous material and you have an ellipse. If you have a sphere, you can rotate it whatever you want. There is no elastic effect. But if you have an ellipse, it is very difficult. It requires a lot of energy to move it like this. So there is also both elastic and electric clamping of domain walls. But we usually discuss only electric. However, the elastic one can be even stronger and shouldn't be neglected. Let's see now what this picture is telling us. So let's look at, we will discuss in a second NBT. In niobium doped material, we don't have these oxygen vacancies, and we know that lead is not going so easily to move around. So we don't have a good explanation what's happening there. I will come with an explanation later, but let's see what we have at this point. So at weak fields and strong fields, we have that we have a very little domain wall motion in hard material, in acceptor doped material, and basically if you look polarization as a function of electric field, you almost don't have any hysteresis. So if domain walls move, they move in such a way that they move like a membrane and come back when field is zero. So they follow exactly the same path. There is no stopping them in some intermediate position. The hysteresis is absent. Okay. When I apply, if I apply bigger fields, then I will start opening the hysteresis as I explained before. But every time I come to zero field, the domain structure will come back because of these dipoles to exactly the same position. So this is large field response. If you look at a soft material, both at weak fields and at large fields, you have a big hysteresis. So field here is small, it's same here and here. There is no hysteresis here at all, and there is a very large hysteresis over here, which is very interesting. And then for other compositions, as we go from 1% iron to 0.1 to undoped, 0.2 niobium, 1, we have almost continuous change in the properties, and something similar also happens at large fields. So we know for a soft material, you remember the Rayleigh law that we discussed before, we know that we get this behavior if domain wall sees random potential, where pinning centers are randomly distributed. They have random strengths that are seen by domain walls. So we can propose the following picture. In hard material, an acceptor doped material, where we have oxygen vacancy, the domain wall will sit separating two different polarization directions, and defect dipoles are aligned with the polarization. If I apply small field, this domain wall bends and snaps back to the same position. If I apply large field, I may start moving these domain walls, with these dipoles, orienting them as I move domain wall in this direction. But there is some kind of a memory which will force material to come back to the same zero polarization state once the field is removed and the non-hysteretic state. It's an experimental fact. For a soft material, donor-doped, niobium-doped material, we see that structure is, we draw conclusion from this experiment here that defect dipoles must be randomly distributed in space with the different strengths. And therefore, the domain wall moves in a potential like this, while in a hard material, it is domain wall is really sitting in a very deep potential. This is valid for weak fields. Of course, this break at large fields. Okay, so that's picture that we can propose, and now we have to prove it and find additional experimental evidence that this qualitative model actually works, and that we will do next.